Hello. In this video, we'll cover section 7.2, which is on measuring survey quality. How do we determine whether a survey is likely to be accurate? It is difficult to judge whether a survey is accurate based only on the outcome of the survey. That's because the parameter, the object that we're estimating with the survey, is unknown. We cannot directly compare the survey results to the parameter to determine how well the survey did. Instead, we evaluate the method that was used when conducting the survey. We evaluate survey methods by considering the expected outcome if the survey was repeated many times. Survey methods have two characteristics. First is accuracy. That's the closeness of the survey result to the population parameter. Again, that's what we're trying to estimate with the survey. And precision, the closeness of the survey results to each other. The goal is to have a survey method that produces results that are both accurate and precise. This can best be illustrated by comparing the survey method to a golfer. A good golfer is both accurate, hits the ball near the cup, and precise, hits the ball in the same area every time. So we can look at four different cases here to see the differences in the method characteristics. So in the first one, we have a golfer who is both accurate and precise. Okay, they're accurate in that they are hitting their shots near the cup, and they are precise in that their shots are clustered in a small area around each other. Okay, in the second case, we have a golfer who is not accurate, but is precise. So they're not accurate in that their shots are not clustered around the cup. However, the shots are in close proximity to each other, so they are precise. So this golfer is precise. In the third case, we have a golfer who is accurate, but not precise. So their shots are clustered around the cup, but their shots are very widely distributed, widely spread out, okay? And so there's not a lot of precision. And then in the fourth case, we have a golfer who is neither accurate nor precise. Their shots are not clustered around the cup, and their shots are not close to each other. Accuracy and precision can be interpreted in survey terms. Accuracy represents the bias of the survey. If the survey is biased, then the survey produces an outcome that is not representative of the parameter. Again, that's what the survey is trying to estimate. This is equivalent to hitting golf shots that don't end up around the hole. Precision represents the standard error of the survey. This is the distance around which we expect the survey results to cluster. If a survey has a standard error of 5%, for example, then we expect the survey results to be within 5% of the center of the survey. We can explore these ideas through simulation. So first, let's look at a very small population. Suppose there are 8 people total, and we randomly survey groups of 4 of them. The people either like dogs or they like cats. We know in advance that 2 of the 8 people are cat people. So that means that 25% of the population are cat people, 2 out of the 8. When we survey the 4 of the 8 people, right, when we go through and grab 4 of them randomly, we could end up with no cat people, right? So if there are only 2 out of the 8, then if we grab 4 at random, then we could grab 4 where none of them are cat people. Or we could get 1 of the cat people, or we could get both of the cat people, right? So if you look at these in percentage terms, when it comes to the survey, our survey could show 0% cat people, 25% cat people, or 50% cat people. And that gives you a range of outcomes, for interpretation when it comes to looking at the survey results. If we perform this simulation many times on random groups of 4, and each time we went through and collated these results, we could determine the relative probability for each of these outcomes, right? So if we did that, that would create a probability distribution, which we give this special name. It's called a sampling distribution. So let's say that we did that in this case. We went through and did this millions of times, and we ended up going through and finding the relative probability. So how often do we get 0%? How often do we get 25%? And how often do we get 50%? Okay, well, it turns out that 25% of the time, we're going to get 0 cat people. 57% of the time, we're going to get 0.25 cat people, and 21% of the time, we're going to get 0.5 cat people. So I do want to point out something that has happened here between the previous slide and this one, and that is that I've switched from percentages to proportions when it comes to the number of cat people, right? So if you look on the previous slide, I had 0%, 25%, and 50%. And then on this slide, I have 0, 0.25, and 0.5. So that is going to be common throughout this chapter. Percentages and proportions are used interchangeably, and expected that you can go back and forth between them. And the same thing is even true if you look at, I used percentages here when it came to describing the probability distribution, but in the probability distribution table, you can see they actually used proportions. Okay, so just wanted to highlight that that is something that is going to happen throughout the section. And the only difference between them is you just end up moving the decimal point 2 places when you go from one to the other. So 21% for the probability distribution becomes 0.21 when written as a proportion, 57%, 0.57. As I said, 0.25 cat people, 25% cat people. So anyway, just want to highlight that. Okay, so but as far as the information here, the relative frequency is that 21% of the time we're going to get 0 cat people, 57% of the time we're going to get 0.25 cat people, and 21% of the time we'll get 0.5 cat people. All right, so what can we learn from that? So one of the things that we can learn is that the survey result, all right, so this is the result of the survey, which is we use the symbol p hat, sometimes accurately measures the parameter. Right, so the parameter in this case is something we know. The parameter is this number right here. It's the percent of the population that are cat people. So we know the parameter in this case. It's 25%. So sometimes we actually end up getting 25% from 57% of the time. Actually, we do end up getting an accurate estimate for the population parameter, but sometimes we don't as well. So sometimes you could see, sometimes, although the population parameter is 25%, sometimes we get, our sample gives us 0, and sometimes it gives us 50%. So sometimes it's wrong. So that's one thing to note, okay? The second thing is that the mean of the sampling distribution, the mean of this is 25%, and that is the same as the population parameter itself. All right, so the mean in going through and randomly doing this survey millions of times ends up being exactly the same as the population parameter. This represents the accuracy or the bias of the survey. This is always the case when the survey is unbiased. So the idea being, if you went through and did a survey a ton of times, and then you took the mean of that survey, that is going to be the same as the population parameter itself, the thing that you're trying to estimate itself. Okay, and that does kind of make sense if you think about it, right? If you went through and you had, you're trying to figure out what the percentage of the population that is Democrats, and you go through and you take 1,000 Democrats that are randomly selected, and you figure out the percentage of that group. If you went through and took that 1,000 people, if you took 1,000 samples, if you did that millions and millions of times, and then you averaged all of those results, you would get the exact percentage of the population that is Democrats itself. Okay, so that's a neat result, very cool and very interesting. It's good to know. So that's one of the things that we've learned from the simulation. All right, so what does it tell us? It says that survey results that are different from the parameter should offset so that the parameter is in the middle of the sample distribution. All right, so what that part is saying notice that, so sometimes we do end up getting, our survey does end up nailing the population parameter. When it doesn't, notice it, when it doesn't, that's when we get 0, that's 21%, and when we get 0.5, that's 21%. Notice those are the same size so that they offset, and so we end up having a mean that is directly on the population itself. So if you get results that are below, if your survey result is below the population parameter, and then you should end up getting survey results that are above as well, and that those two should end up offsetting, so that in the end, if we were to do our survey millions of times, we do end up getting the population parameter itself. The standard deviation of the sampling distribution in this case is 0.16366. So again, I'm using a proportion there. If you were to write that as a percent, it would be 16.4%. That's how far the average survey result is from the mean. So that's a standard deviation, just like all the standard deviations we've done throughout the semester. So this represents the precision of the survey, or how spread out the survey results are. All right, so we give this a special name. It's called the standard error. A high standard error tells us that survey results are very far from each other, and then the survey is thus not very consistent. And I would say in this case, a 16.4%, that's actually a pretty big standard deviation relative to, because that's relative to p hat. So that's relative to this number here. So our range p hat goes from 0 to 0.5, and to have a 0.16366 standard deviation on that, that's a huge part of our distribution. Okay, so that's the first simulation. All right, so let's go through and do another simulation and see if we can go through and refine what we've learned. So what happens if we go through and we increase the number of people? Suppose that we have 1,000 people instead of 8 people, and we randomly survey groups of 10, right, instead of 2. The people are still either cat people or dog people. We still have 25% cat people. So there's 250 out of the 1,000 are cat people. And then this time, instead of saying that we're just going to do the experiment millions of times, we're going to say we're going to limit it. We're going to say we're going to do it 10,000 times. All right. So let's have some thoughts before we actually look at the results. So some thoughts. One, the survey results, it should be possible to vary all the way from 0 to 0% cat people to 10% to 100% cat people, right? And that is because since we have 250 cat people out of the 1,000, you could get none of them, right? If you went through and picked 10, right? There's 750 of them are not cat people, so it should be possible to get none of them. And then it should be possible to have all 10 be from that 250. And so we should expect to see survey results that have a wide range of outcomes. Based upon the fact that this is randomly done, we expect the survey is unbiased. So we would expect the mean of the sampling distribution that we end up with to be 25%. And as far as the standard deviation, that's the part where we're not sure. So the sample is larger, the population is larger, does one have a bigger effect than the other? We don't know. So we're going to just kind of have to figure it out by looking at the results. All right, so seeing the results here. So the one thing that's a little weird, so not everything is perfect with the text that we're using, is that they didn't structure this the same as the first example. They went from a traditional sampling distribution where you have percentages for each of these to a frequency table. So you can convert this into a sampling distribution by dividing the frequency axis by 10,000. So if we were to go through and divide this by 10,000, then this would be 0.3. So that's saying that 0.3 proportion, any bar that reaches that height has 0.3 proportion of the total. This would be 0.25, 0.2, 0.15, 0.1, and 0.05. Okay, so a little irritating that they did this, but maybe they're just trying to kind of change things up to make sure that that students are very flexible when it comes to their ability to read charts. Okay, anyway, so what results did we get? So we got survey results that actually, so we guessed that they could vary from all the way from 0 to 100%. Now, again, we jumped from percentages to proportions. Again, that happens, right? So here I did 0% cat people to 100% cat people, and now we're using proportions instead. So we've got, this would be 0 or 0%. Up to, and the highest looks like that we got maybe there is a minuscule amount of 80% cat people in our 10 people, or 8 out of 10, but it's hard to see them. So the one that the highest value that we can actually see is at 70%. Those 70% cat people, or 0.7 cat people. If you look at the mean of this, it's highlighted by this red symbol. That's at 0.25 fulcrum. That's the word I was looking for. It's at 0.2501, which is very close to the 25% of the parameter, which is what we expected. If it's unbiased, then we expect that the mean of our sampling distribution is going to be at the same level as the population parameter. And then the standard deviation itself is 0.1356. So it did decrease. So this is also called the standard error. It's less than the first simulation. So the survey results are closer together when we have a larger population size and a larger sample size. Okay, so what can so we can go through and do a third simulation to try and figure out, is it the population size or the sample size that is causing the change in the standard error? All right, so suppose everything stays the same as in the second simulation, but we increase the sample size from 10 to 100 people. So we're leaving the population alone. Now, if the standard error doesn't change, then it was the population that had that was the cause of the effect. If it's the sample, then we should see a change in the standard deviation or the standard error. All right, so we still have 1,000 people. Some are cat people and some are dog people. 25% are cat people. We still select groups of 10, so not we still, we are going to select groups of 100 now. And then again, we're still going to do this 10,000 times. And boom, we got our result. The mean is 25% as expected. Again, if you go through and repeat this a bunch of times, the mean of your sampling distribution should be the same as your population parameter. Again, they didn't do the table as a traditional type of sampling distribution where these are proportions, but you can translate them into proportions by dividing by 10,000. So this would be 0.2, 0.15, 0.1, and 0.05. Oh, and look at this. The standard deviation has absolutely collapsed all the way down to 4.2%. All right. And so what we can tell from this is that it was the size of the sample that determined the standard error. So if we go through and increase the sample size, then the standard error goes down. All right, so that's good to know. So, all right, so now if we go through and summarize these results, we can see that as long as our survey is unbiased, the mean when performing the survey many times is going to be the same as the population parameter. So I've said that like 6 times. So that's one important result. And then the second important result is that the larger the sample size, the smaller the standard error. So as the sample size goes up, standard error goes down. Okay. It is possible to go through and find the bias and standard error of a sampling distribution without actually creating and running a simulation. All right, so assuming 2 things. The first, the sample is randomly selected with or without replacement. And if the sample is without replacement, then the population is at least 10 times larger than the sample size. So if you've got those 2 conditions, randomly selected, all right, and if it's randomly selected without replacement, then the population has to be 10 times larger than the sample size. Then we can say 2 things. First, bias, the survey is unbiased, right? If it's randomly selected, then it's unbiased. And so thus thus again, we can expect that the mean of a sampling distribution would be the same as the population parameter. And then second, the standard error, we can go through and we can use this formula to calculate the standard error, right? So if we go ahead and take the population parameter, multiply by 1 minus the population parameter, divide by the sample size. I didn't go through and actually label what these things are. So I did put one of them. P is the population parameter, but I didn't put N. N is the sample size. Okay, so you've got the population parameter times 1 minus the population parameter over the sample size. Take the square root, and that gets you the standard error. Okay, so no simulations necessary. We didn't do any simulation. These are just formulas, and we derived these results from the previous examples. All right, so let's look at how could we use this. All right, so we can illustrate this result by looking at the last simulation case. So this time we're not running a simulation. We're not actually doing this 10,000 times. Instead, we're going to rely upon the results on the previous page. All right, so recall the population has 1,000 people. 25% are cat people. We perform a survey on a random sample of 100 people without replacement, and then they're asking us to go through and find the bias standard error. First, we have to check that the conditions are met. So the sample is randomly selected. So you want to read through here and find where it says that. The survey random sample. If random sample is not in the description here, then you cannot go through and use the result that we just looked at. You can't use this previous slide. All right, assuming the sample is randomly selected. That's A. The randomly selected part is the important part of A. All right, and then if the survey is conducted without replacement, all right, so 100 people without replacement, then we need to go through and do a check that the population is at least 10 times the size of the sample. So if you take the sample, that's 100, multiply by that by 10, that's 1,000, and so we do have the population 1,000 is at least as big as 10 times 100, right? Okay, so it does meet that condition. Or the 2 conditions, sorry, both condition A and condition B. It's got the random part and it's got the size requirement when you have without replacement. All right, and so what can we say from that? Using the result from that previous slide, we can say the bias is 0, so there's no bias. We expect that our survey results to be dead on if you took the mean of them, and dead on with the population parameter. And the standard error is going to be 4.33%. So this is a little bit different than the result that we actually got when we did the simulation. But keep in mind, we did the simulation 10,000 times. So that is an empirical result. So we went through and determined it by experiment. All right, where this result is not pure empirical; it's by formula. So this is the actual result, whereas the simulation is an estimate. All right, so let's look at a homework example that's related to this. According to a research report, 35% of millennials have a bachelor's degree. Suppose we take a random sample of 400 millennials and find the proportion who have a bachelor's degree. And they want us to answer 4 questions. What value should we expect for our sample proportion? What should we get for the standard error? They want us to complete this sentence. We expect blank percentage to have a BA degree, give or take blank. And then if we decrease the sample size from 400 to 200, what effect would this have on the standard error? And it wants us to go through and find the new standard error. All right, so question A, what value should we expect for our sample proportion? All right, so since the survey is unbiased, right, and we can tell it's unbiased because it's a random sample, if we repeatedly performed the survey, we would expect to get survey results whose mean is 35%. All right, and now since it's asking us to just guess at what we would get if we just did one survey, if the mean of our surveys, if we went through and did a bunch of them, is 35%, then that would be our best guess. All right, so we're going to guess the thing that's in the center of our sampling distribution. Hopefully that makes sense. That really is relying upon the results from earlier in the semester, right? If you've got a mean of something, then that's the center. That's the thing that's kind of, you could think of as the most common. And so that's the thing that you would guess if someone were to ask you to go through and make a guess. And then what is the standard error? We can just use the formula there. So we get 2.38%. And then they want us to complete the following sentence. We expect blank percent to have a BA degree, give or take blank percent. And so it's just asking you to take the 2 results, previous results. So we expect 35% to have a BA degree, give or take the standard error. And so that's the sentence right there. And then if we decrease the sample size from 400 to 200, what effect would this have on the standard error? And then find the new standard error. All right, so if we decrease the sample size, then we would expect the standard error to rise. All right, so the standard error is inversely proportional to the sample size. All right, so what that means is as one goes up, the other one goes down, or vice versa. And so if we were to go through, and you can actually check that out by plugging in the smaller sample size of 200, and you do get a larger standard error. So sample size goes down, standard error goes up. Okay, and then finally, we're going to summarize in the next 2 slides. So now let's go back to real life. So these are all kinds of hypothetical with simulations and all this other kind of stuff. In real life, we don't perform the survey multiple times, right? So we don't go through and say, hey, we want to figure out what percentage of the population are Democrats. We don't go through and survey the population millions of times with different, groups of 1,000. Instead, we do the survey one time. All right, so however, that doesn't mean that we can't use some of the things that we've learned in this section. If our survey is performed randomly and the population is 10 times the sample size, then we can assume that the survey is unbiased. All right, this does has value in that it tells us that the distance between the sample, what we end up getting from the sample, from the survey, and the distance between the population is going to be due to error and not bias. Right, so that's a useful result, right? So if we're going through and we're estimating the percentage of the population that are Democrats, and like let's say that we knew that was 40%. Now we don't know that, but that's the point of the survey, is to try and estimate that. But let's say we knew it was 40% and we got 38%. We know that the error, that 2% error, that's due to the standard error. That's due to random chance. That's due to the fact that if you were to go through and pick 1,000 people, you're not going to get exactly the same number. You're not going to get the exact percentage in that group that matches with the population parameter itself. So if the population is 40%, you're not going to get 40% Democrats for every 1,000 people that you choose. Okay, it doesn't work that way. There's random chance there. All right, so again, so what we can do is we can go through and assuming we know that our survey is unbiased, then whatever result we get, although we don't know what the population parameter is, we know that any error with the population is due to error only and not bias. So that may be a subtle point, but it is valuable. And then the second thing is when it comes to figuring out what that error is, we don't know what the population parameter is, so we can't use the formula that we had earlier in this video, right? So if you go back a few slides, this formula here, here we go. All right, so notice this has the population parameter in it. In real life, we won't know the population parameter. We're trying to estimate it. That's why we're doing a survey, okay? But however, since we're going through, assuming that our survey is unbiased, it should be close to the population parameter. It should be close enough that we can use it in place of the population parameter in the formula, and that will give us an estimate for the standard error. And so we can go through and estimate the standard error whenever we do a survey by using this formula. We go ahead and take the survey result for the population parameter, multiply by 1 minus that, and then divide by n and take the square root. Okay, and so that concludes the video. That's the stuff. All right, thank you so much for watching, and I'll see you next time.